All right, we're going to continue our discussion of irrational functions with the concept of rational exponents. And this is really just another way to write roots. This first key concept, x to the 1 over n, is the same thing as the nth root of x. So an easy example of that would be the square root of 9, which we know is 3, is the same thing as 9 to the 1/2 power because of our little invisible 2 right there. So we get 3, whether we think of it as a square root or 1/2 power. So we have two forms in which to write the same thing. We have exponential form, and we have root or radical form like that. And they mean the same thing. This next example shows us what happens if that fraction does not have 1 on the top, if it's x to the a over b. The b is sort of like the n in the first concept. It's like the fractional part. It's like the root. So it could be thought of as the bth root of x to the a power, or it could also be thought of as the bth root of x to the a power. That order of operations is fine either way because basically what they both are is x to the a to the 1 over b, or switch the a and the 1 over b because the multiplication can go in either order. So those are what a fractional rational exponent like that looks like. And then one that you probably already know, but just to make sure because it will pop up in this section, a negative exponent results in a fraction. A negative n is the same as a positive n on the bottom. So a lot of people confuse x to the negative n. They think it should give them a negative result. It should actually give them a fractional result. And that number could be a negative. I'm not saying the answer will never be negative, but this right here does not change the sign. It changes it to a fraction and puts that quantity in the denominator. So a few basic examples. This first one, 12 to the 1/4. The instructions there would just be maybe to write it in radical form. This is the 4th root of 12. The 4th root of 12 is some decimal number. 12 is not a perfect 4th power, so I don't know what that number is. I would type it in my calculator or just leave it as the 4th root of 12. Now 64 to the 1/3 could show up on a non-calculator portion of an exam, and the question like this depends totally on the prime factors. 64, if you start to break it down by dividing out 2's, basically, you'll find out that 64 is 2 to the 6th. So we have 2 to the 6th to the 1/3, and based on our rules of exponents, I can multiply the 6 by the 1/3 and get 2 squared. 6 times 1/3 is 6/3, or 2. 2 squared is 4. And finally, 81 to the negative 3/4. It's going to work in a similar fashion, except this one's a negative exponent. So if you break down 81, it's 9 times 9, and each of those 9s breaks into 3 times 3. So 81 is 3 to the 4th. I want to put that, let me squeeze that 4 in those parentheses. 3 to the 4th to the negative 3/4. All right, so that's 3 to the negative 3/4 times 4. The 4's cancel, that's negative 3. And 3 to the negative 3rd is the same as 1 over 3 to the 3rd, which is 1/27th. Okay, I would expect maybe a common error to be negative 27 in that case, just if you aren't careful there about what that negative exponent means. It means fraction, not negative. So there's some basics. Let's move on to some more examples. This topic kind of just has a grab bag of topics that might come up. You're not really learning anything new as far as rules and what to do. We've done most of this with our work in radicals. It's just now that instead of looking like a radical, it looks like a fractional exponent like these. We're really going to be doing the same skills. Let's do some of those examples. All right, so you know when you multiply two powers together, the exponents add. So a to the 1/2 times a to the 2/5. I need to add 1/2 and 2/5. So in order to add fractions, as you've known for years, you need a common denominator. That's 5/10 and 4/10. Add those together to get 9/10. All right, so not a new rule, just with fractional exponents. This bottom one will be subtraction, same idea. The common denominator of 4 and 3 is 12, so that's going to be 9/12 over b to the 4/12. And division of powers results in subtraction of exponents, b to the 5/12. All right, so this one's kind of interesting looking. The fourth root of 9g squared. And the fourth root of 9, this fourth root applies to both of the parts inside. This one's not going to simplify a lot. It's the fourth root of 3 squared. So another way to think of that would be 3 squared to the 1/4 power times g to the 2/4 power. So that's 3 to the 2/4 times g to the 2/4. There's a variety of ways this one could end up looking. 3 to the 2/4 is the same as 3 to the 1/2, and g to the 2/4 is the same as g to the 1/2. We don't want to leave it as 2/4 if it could be 1/2. And both of these 1/2s are just identical to square roots, so what it all boils down to is the square root of 3g. All right, we can keep them under the same square root because it's a multiplication. All right, so I think that's the simplest form of, of the fourth root of 9g squared. Okay, and here's something similar. We have the fifth root of 64 over the fifth root of 4. Because of the nature of these numbers, 64 and 4, our best bet is going to be to think of prime factors and just break it down into smaller bases. 64 is 2 to the 6th, and the fifth root is the 1/5 power. 4 is obviously 2 squared to the 1/5 power. So that's 2 to the 6/5 over 2 to the 2/5, and 6/5 minus 2/5 is 4/5. So 2 to the 4/5 will work, or the fifth root of 2 to the 4th, and 2 to the 4th is 16. So that's a possible answer. That's a possible answer. It just depends on the form that they ask us for. All right, so both of those mean the same thing, one in exponential form, one in radical form. All right, so really this is going to be about as complex as it gets for this section. If I gave you, as of our previous studies, the square root of 2 plus 3 over 1 minus the square root of 5, we would rationalize that by multiplying by the conjugate of the bottom on the top and the bottom. That's because you can't have square roots in the denominator, and remember that a 1/2 power is the same as a square root. So this is not allowed in the denominator any more than a square root is, so we're going to rationalize it in the same way. We want to multiply top and bottom by the conjugate of the bottom. Okay, remember, conjugate is not the opposite. It is, instead of adding the 2, we will subtract the 2. All right, so top and bottom both need to be FOILed. Both need to be distributed double. On the bottom, that's going to make some stuff simplify, fall out, which is why we chose the conjugate. But let's do the top first. X squared times 3, or excuse me, x to the 1/2 times 3x to the 1/2. That is 3x. All right, the 1/2s add to become a 1. It's just like multiplying the square root of x by itself. Minus 2x to the 1/2 minus 6x to the 1/2 plus 4. Okay, all that comes from FOILing out the top. On the bottom, I do 3x to the 1/2 times 3x to the 1/2, and I get 9, times, I see I left my 1/2 off of that. So I get 9x. Then the minus 6x to the 1/2 and the plus 6x and a 1/2 cancel each other out automatically, and then I'm left with a minus 4. All right, notice there are no 1/2 exponents in the denominator. That's rationalized. It doesn't have any square roots down there anymore. That's a good thing. So on top we can simplify some stuff. We can do 3x minus 8x to the 1/2, And that's the same as 8 times the square root of x, but if the question gave it as 1/2, we'll leave our answer as 1/2. Plus 4 over 9x minus 4. And that is as simple as this one can get. There are no coefficients in common that I can cancel. I've solved the problem of having a square root in the denominator, even though it looked like a 1/2 instead of a square root. That was still a problem, and I fixed it with rationalizing. All right, so that's, like I said, that's as complex as this will get for this topic. No real new ideas, just using old ideas with new looking powers with these fractional exponents.